San Diego, California. NASCO, the National Steel and Shipbuilding Company, has delivered over 110 ships to the world's fleets during the last 4 decades. It's here where all manner of huge ships take shape, from oil tankers to container ships. And they all require copper, hundreds of tons of copper. Here, close to 1,200 workers are busy assembling one of 11 identical cargo ships for the U.S. Navy. The first of the ships, the USNS Lewis and Clark, is already in service.
This ship is the newest and largest auxiliary ship in the U.S. Navy. Our length is 688 feet and our width is 106 feet.
Each of these electrically powered ships requires an extraordinary amount of wiring to operate.
There's approximately 500 miles of copper cable on board this ship that is used to distribute electricity for the low voltage systems and then our high voltage systems that run at 6,600 volts, which is used for the propulsion system to drive the ship through the water.
But copper is used for much more than just the wiring of these vessels.
We utilize copper in the paint on the bottom of the ship to prevent marine fouling. We use copper inside the ship in alloys to pipe seawater systems and prevent corrosion on those seawater systems. And we use copper also in the propeller as an alloy to ensure a long service life of the propeller.
Copper is the metal of choice for any part of the ship that comes in contact with the sea. Because of one of copper's most valuable properties, its resistance to saltwater corrosion. Immediately upon contact with water, the metal develops a protective oxide coating. Merchant vessels and warships demand durability, and copper stands the test of time in one of the most corrosive environments on Earth. To make pumps, valves, and onboard desalination systems, the shipbuilders use a special copper and nickel alloy called cupronickel.
In order to prevent the seawater systems from corroding, we have constructed them out of copper nickel, and that copper is very resistant to corrosion. When seawater is piped through a copper nickel pipe, you actually get a layer forms on the inside of the pipe of oxides that then stop the corrosion process.
The alloy is generally 70% copper and 30% nickel. The addition of nickel increases both copper's strength and corrosion resistance. Copper is also alloyed with harder metals to make one of the strongest and largest parts of each ship. A 22-foot wide, 40-ton corrosion-resistant propeller. The naval architects who fabricate such massive propellers use a centuries-old casting technique, combined with some new manufacturing technologies.
Propellers are cast in one pour generally, and then when the casting is completed, the mold is taken off, and then the cast propeller would be cleaned, sanded, and then shaped. Rather than having to build a model of a ship, they can do that with a 3D model now and generally get a fair idea as to how the impact of the design is going to work against the hull.
Once the propeller is shaped and cast, then it's machined to a very fine tolerance. They have to be able to shape the propeller blade profiles to an exact shape to ensure long service life, prevent vibration, and also prevent noise, which can create problems for the vessel.
Although copper alloy propellers can withstand years of seawater exposure, they can still be damaged by ocean debris. Engineers routinely inspect used propellers with staining chemicals and magnifying glasses to find even the tiniest flaws.
A small crack can promulgate out, and you can have a catastrophic loss of blade section based on the small crack being allowed to not be repaired and grow. We do a visual inspection, and then based on that visual inspection, we will determine what the customer needs for the repair. Generally, it'll be welding, grinding, balancing the propeller.
Copper also protects vessels from tiny but dangerous sea creatures that, given enough time, could even sink a ship. Copper is antimicrobial, meaning microorganisms can't survive on it. Scientists theorize that copper kills microbes by damaging their DNA. It's been used to protect ships from marine organisms since the 18th century, when the British Royal Navy first clad the hulls of their wooden warships with copper sheet. Copper protects timbers from sea worms that can bore through hulls. It also repels barnacles, which create drag.
Nowadays, with the steel hulls, we still need something to prevent sea life from adhering to the hull, and they use a copper paint, or a paint with copper in it. And the copper basically prevents any sea life from wanting to grow on the side of the ship.
Through the centuries, shipbuilders have continually taken advantage of copper's benefits at sea. One of America's most notable ships, the USS Constitution, often referred to as Old Ironsides, was actually clad in copper, not iron.
When the ship was built in Edmund Hart Shipyard in 1794 to 1798, they sheathed the bottom of the hull of the ship with copper. This original copper, when she was built, was supplied by Great Britain. We actually imported it. Paul Revere actually supplied the original copper bolts and fasteners on board the ship during construction.
In 1803, when the sea-worn vessel came to port for repairs, Paul Revere decided it was time to make copper sheeting in America.
When the Constitution was refurbished in 1803, Paul Revere, thanks to help from the government plus his own money, developed a rolling process in Canton, Massachusetts, and rolled the copper. So the second sheathing of the Constitution was done by Revere metal with Revere metal made in this country.
The hull isn't the only place on the ship where copper sheeting was put to use. Another small but critical area was completely lined with copper.
This is where young boys on board the ship would come down during battle to retrieve about 6 pounds of gunpowder, which would be in this powder magazine, which is lined with copper. Copper is a non-ferrous metal. It wouldn't spark as easily, and you can imagine with all the gunpowder down below, if there was a spark, it could ignite the whole ship and you could actually lose your ship.
Though copper's merits at sea have been known for centuries, we've been taking advantage of the red metal's array of attributes for close to 10,000 years. In that time, copper has helped revolutionize our technology. Today, copper is all around us.
Everything that you touch during the course of the day will have copper in it or have some connection to copper. We have copper in our phones, copper in our computers, we have copper in our bodies.
Copper is vital to our modern way of life. It's used in electric motors, it's used in copper tubing, it's used in copper wiring. Without all of these things, society would not be at the level that it's at. It's one of the building blocks of making our world as industrialized as it is.
Beyond copper's ability to resist corrosion, kill bacteria, and conduct both electricity and heat, it's also beautiful. In some applications, its veneer is the focal point, such as in sculptures and roofing.
We're drawn to copper alloys, because of its soft color, its warmth, the ability to change its color, change its shape. It's probably one of the few applications of the product of metals that's exposed and gives you that warmth.
In fact, it was copper's distinct red color that first got it noticed.
Copper was one of the first metals that was discovered by man nearly 10,000 years ago, and the reason why that is that copper is one of the few metals that actually exists in the metallic form in nature. So ancient man might have been walking along and seen some small glint of metal and been able to pick up and find that they have a piece of a metal that is easy to form, it's soft, and this material would have been easy to form to a variety of shapes.
By about 3600 BC, the demand for copper increased, for use in items as disparate as jewelry and arrowheads. The naturally occurring deposits on the ground became scarcer, But the ancient Egyptians discovered a process called smelting, which separated the metal from the mineral ore in which it was embedded.
The very earliest forms of smelting would simply have been taking the metal and heating it up over a fire that was sufficiently hot for the metal to melt, and the smelting would occur naturally by the burn-off of some of the impurities. By trial and error, the civilizations later realized that you could add certain things to that molten metal which would cause the impurities to be removed preferentially. If you add an addition like charcoal, which is basically carbon, then what might happen is that the carbon would combine with the oxygen in some of these impurities, and that would burn off as carbon dioxide, carbon monoxide, leaving the unoxidized metal behind.
At about 3000 BC, the ancient Egyptians inadvertently created a completely new metal when some tin was mixed in with the copper.
Copper and tin makes bronze, and that's the root of the expression, the Bronze Age, the period in which people were starting to work with these materials and to make an ever more complex range of artifacts out of these metals.
The development of bronze was a milestone in human history because pure copper is relatively soft, but bronze is harder and stronger. Farmers could now make a wide array of sturdy tools, and warriors could craft weapons with lethally sharp edges. Without a doubt, the army with the most bronze swords and armor held a distinct advantage. For many centuries, bronze reigned supreme. Then, from Rome onwards, iron became the basic metal for every Western civilization. But copper would make a spectacular comeback. Copper, mined from vast ore deposits, was destined to connect and energize the world. At Arizona's Phelps Dodge Sierrita copper mine, trucks are hard at work, hauling ore. These mining trucks are some of the largest dump trucks in the world. They can haul as much as 260 tons of ore in a single load. Yet these house-sized haulers couldn't budge a pound of copper without copper.
In one of these haul trucks, there's a lot of copper. You'll find it in copper wiring that runs throughout the truck to run the lights. We also use it in the alternators. We also use it in any motors that are on board of the haul trucks. Of course, there's a lot of copper in the radiator, which is a vital component to keep the engine cool.
The radiators of the largest mining trucks use 2,500 pounds of copper for tubing and fins. It's here where copper demonstrates another of its unique properties. It conveys heat better than almost any other metal.
Copper is used because it has such a high thermal conductivity. The heat in the water, which comes from the engine, is transmitted to the copper, which sets up lattice vibrations, which move through from the water side of the copper radiator to the air side, and is transmitted out.
Phelps Dodge runs a total of 5 mines in the southwestern United States. Together, they produce more than 2 billion pounds of copper annually and account for about 60% of total U.S. copper production. Their mining and refining process has many steps.
The mining process begins with the discovery of an ore body through exploration drill holes. We determine where we need to go to extract the ore. We use large blast hole drills to drill 65-foot deep holes.
After the blast holes are completed, the explosives crew gets busy. Laying charges is both a high-tech science and a choreographed art.
At the end of this electronic detonator, there is a computer chip. You are actually programming the firing time into the detonator. They need to fire in a sequential time.
To all units, this is a 1-minute blast warning.
Fire in the hole for 1 shot.
After the ore has been loosened, the shovels can dig in.
Each one of the buckets of material in that shovel weighs approximately 65 tons. So in about 4 scoops, that shovel can load one of our 260-ton haul trucks.
If the ore is mined closer to the surface, the copper within the ore has been exposed to oxygen. Oxidation converts the copper to copper oxide. The copper oxide atoms are not bound as tightly to the ore as copper, so they can be leached out of the ore.
What we're doing behind me is sprinkling a weak acidic solution onto some material that contains copper oxide. And the solution contains sulfuric acid. This comes in contact with our ore, and it converts it into a solution of copper sulfate. The copper sulfate then travels down to one of our processing facilities where we ultimately extract the copper.
Ore that's not a candidate for leaching takes a different processing path.
The rock that's deeper down in the ore body is a sulfide, and it is not leachable by acid, so we have to separate it by flotation.
The first step of the flotation process is to get the rock down to a manageable size.
Gyratory crusher is a large cone that fits inside of a cone-shaped cylinder, and it literally wobbles around, and when a rock gets in between the walls of the mantle and the liner, it crushes it by wobbling around.
Before the ore can be refined, it must be ground down to the consistency of sand in massive drums called ball mills. Each 16-foot high, 19-foot long mill is filled with softball-sized steel balls that pulverize the ore. At the same time, water and chemical agents are added to the mix, creating slurry.
We then put it through a machine where we agitate the slurry with bubbles and reagent, and the copper mineral sticks to the bubble, floats to the top. We scoop it off and then filter off the water and send it to the smelter. At the smelter, the concentrate is heated, it's melted, and the copper material separates further.
The metal leaving the smelter is 99.6% copper, but not pure enough for most electrical applications. This impure copper is cast into slabs, called anodes. The anodes are further purified using a process called electrorefining. In electrorefining, racks of anodes are suspended in an electrified acid solution for 10 days. During this period, the copper dissolves and is attracted to a negatively charged cathode, leaving any impurities behind. The resulting cathode is 99.99% pure copper. A similar process called electrowinning is used to extract copper from liquid copper sulfate that comes from the leaching process.
In the electrowinning process, we use electricity that charges the ions in the solution. That causes the copper to plate out as a solid. If you could see inside the electrowinning cell, you would see little electrons and protons on the copper. You'd see the copper moving towards the starter sheet and actually plating it, actually attaching and becoming a solid. Over a period of 5 to 7 days, the copper gets thicker on the starter sheet until it's heavy enough for us to actually pull out and remove the copper.
These 200-pound cathodes are also 99.99% copper. The mining and refining operations run 24 hours a day, 365 days a year. Like most copper mines, the ore that's mined from Sierrita has a low percentage of copper in it. Each ton of ore yields just 6 pounds of copper. But many copper products don't rely on a supply of virgin metal from the mine. About 1.5 million tons of scrap copper are recycled every year.
Copper is one of the metals that is 100% recyclable. And most of the copper and copper alloys that you have around you today are recycled from previous copper applications. You could be using copper tube in your house today that has recycled material from the jewelry that Cleopatra wore years ago.
Recycled copper can be used for almost anything except for electrical wire, because refining the metal back to near 100% purity isn't cost-effective. One of the big consumers of recycled copper is the plumbing industry. Plumbers frequently choose to install copper pipe because it's naturally corrosion resistant. It frequently outlasts the building in which it's installed. Forming the copper pipe, or tube as it's referred to in the industry, is a fairly straightforward process.
Everyone picks up a tube of toothpaste in the morning, squeezes that tube of toothpaste, and it comes out the tube. Making copper tube is the same thing. We take a billet of copper or a slug of copper, we put it through an extrusion press, which is the toothpaste tube. We squeeze it under very high pressure, and copper tube comes out the end. But the only difference is that we use a mandrel or some method to make sure that there's an opening or a hole in the center of the copper tube.
Modern plumbers weren't the first to notice copper's plumbing potential.
The Egyptians produced some of the earliest copper plumbing. What they probably didn't realize is that in addition to having a material that they could form into plumbing pipes, they were actually purifying their water at the same time, and that the antimicrobial properties of the copper were killing bacteria and contaminants within the water.
Today, copper's antimicrobial properties have compelled medical experts to study the metal's potential.
We understand that through research, ongoing research, that it has the ability to kill certain pathogens. In a situation where it was with copper, you would see over a very short period of time that the copper would not allow the bioload or that product to grow. It would actually bring it to an end.
In the near future, copper may be showing up in hospitals on doorknobs and handrails to stop the spread of bacteria, such as Staphylococcus and E. coli. Copper isn't just used to build practical items. It's also used to create everything from the biggest bells to national icons. This is the World Peace Bell. 12 feet high and 66,000 pounds. It's the largest swinging bell in the world. Located in Newport, Kentucky, it was built to commemorate the turn of the millennium. Like most bells, it's made of a copper alloy, often referred to as bell bronze.
The World's Peace Bell is made of 80% copper and 20% tin. The reason bells are made of 80% copper and 20% tin is the quality of sound. Up until around 1600, they experimented a lot with different copper, zinc, tin, and it was determined that the combination of 80% copper and 20% tin produced the best sound.
The bell was made the same way bells have been made since the Middle Ages. Molten bronze was poured into a mold. But pouring metal for a bell this large presented a daunting new challenge.
We had about 80,000 pounds of metal ready to be poured. We calculated that it had to be done in 4 minutes and 54 seconds. If it was too slow, we'd end up like the Liberty Bell in Philadelphia. If it didn't cool uniformly, the danger would be that the bell would crack the first time it would hit because the metal would be inconsistent. The final cooling stage would be inconsistent.
The bell's designers from Verdun Bells in Cincinnati, Ohio, held their breath the first time the switch was thrown to release the striking hammer.
Of course, we were all worried about what would happen. We hoped we didn't have another Liberty Bell on our hands. 18 seconds before midnight, the switch was turned on, and it struck right on it. At the first strike, we knew it was good.
Verdun Bells has been making bells since 1842. Today, it operates the oldest bell foundry in the United States. It makes about 250 large bells each year, used mostly by churches and universities. It casts bells using a method it developed which uses sand instead of clay to make each mold. Sand is more efficient, as it dries and hardens much faster. The sand is formed into a bell shape using an aluminum pattern.
What we're doing is we're packing the sand nice and tight so that it'll create that perfect cavity that the bell is sitting in. This sand will get really hard like concrete. Then we'll roll this thing back over and you'll see the inside profile of the bell. That's when we'll put that piece of the flask on and we'll put more sand in, do the exact same thing. Then when we break the flask apart, we'll pull the pattern out. That way we can restack the two pieces of flask together and create a hollow cavity that's the exact replica of the inside of the bell and the exact replica of the outside of the bell.
We then melt bronze, bring it up to 2200 degrees, pour it in the sand mold, wait for it to cool, break it out, and then the arduous task of cleaning it up starts. As it comes out of the cores, when we break it loose, it's not very good looking.
Verdon also uses bronze to make statues. For centuries, artists have valued bronze for its beauty and durability. Some statues are cast using a process similar to the one used to make bells. But other statues, including America's most revered of all, the Statue of Liberty, are made with pure copper.
It looks like it could be a solid piece of copper, but it's not. Inside is an iron tower that was designed by Eiffel, and that is what is referred to as an armature. It's a fairly complex support structure that holds the skin of the Statue of Liberty.
Lady Liberty's skin was sculpted from over 160,000 pounds of pure copper sheet. Before the skin could be riveted onto the iron armature, each of the 300 plates were hammered into shape using an ancient metal smithing technique called repoussé. This process is still used to form intricate details. Coppersmith Larry Stearns is using it to fashion a rooftop ornament called a finial.
Repoussé is a process of hammering sheet into a negative form. To perform the repoussé technique, you start with a blank of generally soft copper and start hammering it into that form. As you hammer it, it becomes harder and harder to the point where it will become brittle and split. So typically you are also doing a process called annealing.
Annealing is simply heating up the copper. But the science behind the process isn't so simple.
In copper, the atoms are arranged in a particular crystal structure, and there comes a point where the only way that you can continue to deform the material is if you allow the rearrangements to occur at the boundaries between the crystals. And in annealing, you heat the material up to a temperature that's below its melting point, but high enough for the atoms to be able to rearrange themselves. And then you can deform the material again. And so that's why in copper you need to be able to work and anneal and work in a repeated fashion.
I still have a long way to go, but you can see that the shape is starting to develop.
Though copper can be fashioned into ornate shapes quickly, it can take 10 years or more for the signature copper green, called patina, to form.
Patina is actually a crystalline structure that builds onto the surface of the copper. After several months of wet weather, the surface will be a pretty uniform brown, and it is stable in that color for up to 10 to 15 years. And then you will start seeing a very slight hint of the green building.
For those who just can't wait, there's a way to accelerate nature's pace. Coppersmiths can apply ammonium sulfate or other oxidizing chemicals that speed up the patina process considerably. Bright copper ages within minutes. But the stately green color of a weathered copper roof isn't the only reason homeowners invest in copper roofing.
Properly installed standing seam copper roof in 16-ounce copper will last 100 years. You can install a roof and not think about it for another 100 years versus an asphalt shingle, which might go 15.
But you'd better have a fat wallet. A copper roof for an average-sized house could set you back as much as $30,000.
Copper has proven its durability because we can look at the cathedrals in Europe from hundreds and hundreds of years ago where that same copper on the roof exists today.
The chemical process that causes copper roofs to develop a patina coating is the reason they last so long.
Patina is nothing more than what we would refer to in iron as a rust. And what it does, it forms a barrier between the atmosphere and the base metal to give us a protective coating.
Roofs and bells showcase how copper is an ideal medium for large projects. But copper can go small, too. You'll find it in almost every piece of electronics. Integrated circuits, more commonly called computer chips, are at the heart of everything electronic. In the last decade, copper circuitry has enabled chips, and thus the multitude of electronic devices therein, to become smaller and more powerful.
In the beginning of the integrated circuits, aluminum was used because it was really the best material in terms of being compatible with the rest of the integrated circuit technology. Copper was always known historically as a very good metal for interconnection. However, it had some negative properties. If it comes into contact with the actual devices, it can change its properties, so it wouldn't behave as the integrated circuit was designed to behave.
By the mid-1990s, aluminum circuitry just couldn't get small enough to fit within shrinking electronics. Aluminum's resistance to the flow of electricity means more of it, and more room for it is needed to conduct ample current. Engineers knew that copper's lower resistance allowed for much smaller wires, but they had to find a way to protect the silicon from the copper. After nearly 15 years of research, scientists at IBM finally developed a microscopic barrier that did just that.
It's actually called a barrier layer that would keep the copper sort of on top of the devices. And so it wouldn't be able to go down to the actual device layers.
This advance made it possible to fabricate smaller chips that run up to 40% faster and use 30% less power. Installing the copper interconnects onto the silicon chips involves relatively common metalworking processes, but on a microscopic scale.
We use electroplating, just like they did in the old days, to coat the bottom of a cooking pot with copper, but with certain chemicals that allow the electroplating process to just perfectly fill all of these trenches with copper metal, and those are our interconnects. It's 1,000th the size of a human hair.
Chip assembly takes place in what's called a clean room.
We can't tolerate any speck of dust because that's larger than the interconnects we want to make. It would block their fabrication and cause a defect that would kill the circuit.
It wasn't by accident that copper connectors ended up in the newest computers. Since the power of electricity was first harnessed in the late 1800s, the leading use for copper has been for the distribution and control of electrical current. A neutral atom of copper has 29 electrons. It's a good electrical conductor because a copper atom gives up its outermost electron easily. This 29th electron moves freely from the vicinity of one copper atom to another.
If one could see inside the structure of an atom, then what you would see is electrons that were drifting through between the copper atoms, but almost unimpeded. Whereas in other metals and non-metallic elements, the transfer of electrons has to happen more specifically by the electrons hopping from one atom to the next.
It's very easy to accelerate electrons in the presence of an electric field. As a result, copper wire is extremely sensitive to electrical pulses. Only silver conducts electricity better than copper, but copper is much less costly. Today's world is crisscrossed with a lattice of electrical wires, bringing power to homes and businesses. copper is used almost exclusively for all wires, except those spanning long distances. Aluminum works better for those, since it's lighter and keeps overhead lines from sagging. Cerro Wire in Ogden, Utah, manufactures a variety of wire gauges for use in homes and businesses. The different sizes are drawn to a precise and consistent diameter through a series of dies, each one smaller than the last.
It's not as simple as stretching it because you can't control the process if all you're doing is like a taffy pull going from a large size and pulling it down. You have to control the physical diameter. When you go to the next die, you're taking another 25% cut, and you have a perfectly round, perfectly sized diameter when you go to the next die.
Cerro wraps multiple strands of copper together to create the cables that will be used to transmit larger electrical currents in commercial buildings.
Because the commercial products carry so much higher voltage and amperage, they're composed of stranded conductors so that we maintain flexibility.
Copper cables deliver more than electrical power. They also deliver communications. In 1866, the first transatlantic cable succeeded in carrying a message 2,500 miles from New York to London. The core of the transatlantic cable consisted of 7 strands of the best quality copper wire. Although silica glass fibers have supplanted copper as the signal-carrying medium, there's far more copper than glass in the latest transoceanic cables. The cables are sheathed in copper, which carries power to pumps. The pumps power lasers, which convey the information. The copper also protects the data by creating an electromagnetic shield that blocks stray signals. Like other electrical devices, the cables require pure copper. But new copper alloys are expanding copper's reach beyond the world of electronics. The industrial importance of copper in the 21st century has been extended by the ease with which it combines with other metals. Tin and zinc have long been principal alloying elements. But now there are many others, including aluminum, beryllium, chromium, and manganese. They form alloys with unique mechanical and physical properties. Over 400 copper alloys are in use today. In the near future, one new copper alloy may be showing up in a tag sewn into your clothing and attached to almost all of the products you buy. Engineers are working on a mixture of copper, nickel, and silicon that will maintain copper's conductivity, but will also be strong enough to support tiny antennae, only 35 microns thick. That's 1/10 the thickness of a sheet of paper. An antenna embedded in a tag will transmit information about you or a product to a computer to inform the retailer about your consumer preferences or the status of its inventory. Ansonia Copper and Brass in Waterbury, Connecticut makes specialty alloys for customers with very specific requirements.
One of those alloys would be a particular alloy we make for the aerospace industry, where the customer needed good electrical conductivity, strength within the wire so that it could withstand constant use, and also to go from ground level to 45,000 feet in the air, where the material actually grows because of the change in altitude.
The custom alloy, which will be used to make airplane struts, is composed of 90% copper and 10% aluminum. In this application, the aluminum adds hardness to the copper. The production process is monitored every step of the way, because even a slight variation in the predetermined formula could result in a catastrophic failure for one of the airplanes. Before and during the casting supervisors take samples to ensure that the mixture is exactly right and free of impurities.
We take that sample and we pour it off and we make a slug, and then we send it over to our analytical laboratory and we take it through an analysis process to determine are we on analysis at this time? If we are, we go ahead and pour. If we aren't, then we make corrections back in the melting furnace.
Chemists in the lab quickly assess each sample. One instrument they use, a spectrometer, analyzes the atomic composition of each sample. After a laser slices some atoms from the sample, a light is then filtered through that sliver of atoms. The light projects a prism of colors. Each color represents an element. The amount of each color tells the chemists how much of each metal is in the sample.
And this sample represents 7,600 pounds of metal in the casting shop. We have about 20 minutes to determine 25 elements and report to the casting shop.
After an alloy is cast and shaped, further tests analyze more of its physical properties.
The tensile tester actually pulls the material, and it's measuring the amount of strength it takes to pull the material until it actually breaks. That defines the ductility of the material. All the alloys that are produced here have a specification, and we have to produce the material and make it to that specification.
Just as the ancients who first combined copper and tin couldn't have predicted where bronze would take them, 21st century metallurgists can only guess where the new alloys will lead us.
It has been around for such a long time that we have learned what we think are most of the technologies, but we only think that. We're sure, beyond a shadow of a doubt, copper will be an integral, instrumental metal in everything that we do from this point forward. The same properties that we know of and use will continue to allow us to use it in the new technologies in the future.
Count copper among the marvels we seldom celebrate, but have helped advance the march of our technology. This largely unsung metal and its alloys promise to keep pace with our ability to mine technological treasure from nature.